Okay, good afternoon. So we're going to talk about transistor level design of the critical PLL circuits. By now you're very familiar with a PLL. It takes the reference frequency, compares it to the a feedback version of the output frequency, a divided version, determines if there are phase or frequency errors, converts those into signals that drive the charge pump. The charge pump then creates charge packets that are integrated on the loop filter to figure out what the correct tune voltage is to tune the VCO. In this talk, I'm going to focus on transistor level design of those blocks that are designed in a full custom manner. I'm not going to spend time on those blocks that are done in a more automated design flow, which could be the sigma delta modulator, for example. I'm also not going to talk about crystal oscillators, which are very often specialized design or off-chip components, and I'll spend only a little bit of time on the buffer design. Most of the time will be spent on discussing VCO design, programmable dividers, phase frequency detectors, the charge pump, and then the loop filter. I'm going to try to explain or tie transistor level trade-offs to system level specifications, and also introduce some challenges related to nanometer CMOS design of these building blocks. So if you look at the output spectrum of a PLL, we have its center frequency f0. Around the center frequency, we find that the properties of the signal are largely determined by the reference signal. As we step away a little bit from the center frequency, we notice a noise pedestal, which is set by in-band phase noise. We're within the bandwidth of the PLL, and primarily phase frequency detector, charge pump, filter, and divider contribute to this noise pedestal. As we then go out of the loop band of the PLL, the VCO starts to dominate the properties of the noise. And we can also see reference spurs, which are set by properties of the loop filter, the phase frequency detector, charge pump, and the KVCO. Far out, we have wideband noise, which can come from the VCO or from the buffer amplifier we use. We primarily focus here on frequency synthesis application. We are interested in the spectrum because it relates to receiver blocking specifications or transmitter mask, the spectrum mask that we need to meet for our transmitters. And we are also interested in the integrated noise because that relates to the modulation specifications that we face. The first block I'm going to discuss is the voltage-controlled oscillator. Voltage-controlled oscillators are very important because in the integrated noise, they will contribute about half of the integrated noise, so they require a lot of careful design. When we have to choose between different oscillator design styles, we can basically choose between ring oscillators or on-chip LC oscillators. I just have two diagrams here of some basic ring oscillators, a single-ended version, which we can tune maybe through the supply, or a differential ring oscillator with 4 stages and a cross-coupling within the loop, which we can maybe tune with a current source. Now, these oscillators only use active components, have very small area, they can be tuned easily, but that also means that any disturbance will move the frequency around a lot, and that results in fairly poor noise properties. On the other hand, we can put LC tanks on a chip. They, however, require quite large area, but they give us much higher frequency stability, but it also means that it's harder to tune these oscillators. However, for applications like frequency synthesis or high-speed serial links, we need very stringent phase noise requirements. And for example, based on this work of the paper of Professor Abidi, if you compare the current that you need in a ring oscillator compared to the current that you need in an LC oscillator to meet a certain carrier-to-noise ratio, he calculated that the current of the ring oscillator can be 50 Q² times larger than the current of an LC oscillator. So clearly, for anything where we have stringent noise specifications, we tend to use LC oscillators. In clock generation, ring oscillators might be used more. So now that we want to build an LC oscillator, we want to start looking at how to make an electrical resonator on a chip. We typically use differential center-tapped inductors on the chip. It has 2 input ports, P1, P2, a symmetrical layout, and then a center-tap port, P3 here. Electrically, we indeed find that it has inductance. Also, however, we see that there is series resistance in the structure because of losses in the wires, losses in the substrate that also result in energy losses and reduced Q. And we also notice that at higher frequencies, the signal might bypass the inductor through capacitance due to the crossover here or capacitance of interwire capacitance in the windings. Additionally, the inductor sits on the substrate and has capacitive coupling to the substrate. The substrate can be highly resistive, which is desirable to get low losses or low inductive losses in the substrate, but that means that we can get high electrical losses when we have to pass this through this resistor through these capacitive parasitics here. Very often people will insert a patterned ground shield. It's a little light here, but it's underneath the inductor, and it basically makes for a good termination of the electrical field lines to a good ground so that we can bypass the losses or the electrical losses through these substrate resistances. In nanometer CMOS, you can get inductors of a few nanohenry, which will have quality factors between 5 and 15 maybe, and which, however, require areas which can be as large as 150 by 150 microns square. Now that we have an inductor, we want to make a resonator, so we take maybe some fixed capacitance and we put it in parallel with the inductor, and electrically now we get this diagram here. Note that we will focus on the dominant components, the inductors as well as these two capacitors, and we will assume that the parasitics are small enough. At that point, we get an electrical resonator who has an impedance as function of frequency, which we see here. The impedance will peak around the resonance frequency, which is given on the right here as 1 over the square root of L times C. At resonance, we see equivalently resistive impedance of the tank. That is given by Q times the characteristic impedance of the tank, and that the characteristic impedance then is given by the square root of L over C. Of course, to make good oscillators, we actually want to have as good resonators as possible, which means that we want to see high quality factors in the resonators. And high quality factors, or the quality factor better of the resonator, is a combination of the quality factor of the components, more specifically of the quality factor of the capacitor as well as the inductor. In fact, if you look at the formula, the smallest quality factor will dominate the quality factor of the overall tank. At lower, the quality factor of inductors tends to increase with frequency to the first order, and so whereas the quality factor of the capacitor tends to decrease with frequency. What we see is that at lower frequency applications, very often we are limited by quality factors of inductors, whereas for higher frequency applications, the capacitor quality factor can be an issue, or also when we have widely tunable oscillators. So now that we have a resonator, we want to make an oscillator. We need to make sure that although there are losses in the resonator, we need to provide extra energy so that the oscillation keeps going. Also that the oscillation will start up when we apply power to the oscillator. So we have the structure here, L's and C's, and now we attach to it a differential pair, but we cross-couple it with positive feedback. So electrically, we have around resonance, we have the L, the C, and the RP. And then this structure around its bias point can be modeled as a negative resistance. So when the circuit biases up at startup, at the beginning of power up, what will happen is that, or what we need to study now is what the effect is going to be of small noise impulses that are present in the circuit due to the presence of these active components, and how they will be treated by the resonator, which has this negative resistance in it. When we analyze this, the analysis on the right here, we notice that this structure will have two poles, two conjugate poles, and in fact, if we make the GM of the negative resistance sufficiently large, in fact, we want to make it 2 to 3 times larger than the loss of the resonator, we find that the poles are well into the right half plane, and that means that if we look at the response of the structure to small noise impulses, that we get an oscillatory response with an exponentially growing amplitude. So when we follow these rules, we have a system now that will reliably start oscillating when we apply power to it. Now, of course, this exponential rise cannot continue. It will have to stop at some point. In this example, for this particular oscillator, what will happen is as soon as the voltages become very large, the currents in to the transistors will the bias current will completely switch between either transistor. So if you look at the current waveforms in the transistors themselves, which are shown here, after a while we see that they become square waves. If we model this, we find that we have a differential square wave going into the tank, and then we have some two constant common mode components. Now, this square wave of current goes into an impedance that is a filter, as we have seen from the previous slide. The impedance of the resonator is only high around its resonance frequency, and the higher frequency components of the currents will be attenuated. So if you look at the fundamental component of this square wave, we actually find that it is 2 over pi times I bias, and it gets multiplied with the RP of the tank, and so that gives us then the differential amplitude of this oscillator. So far, we have been assuming that in the current limited regime, which is shown here, we have the dependence of the amplitude versus the bias current. And we are assuming that we are current limited, which means that the amplitude is indeed set by this bias current, and as we increase the bias current, we get larger amplitudes. Of course, at some point, more in particular when the swing here tries to go through zero, this bias current will be crushed and we will hit a limit. We will actually move into what is called the voltage limited regime. Now, given that the common mode of the signal is at VDD, we can actually have a maximum differential amplitude, which will be in practice somewhat smaller than 2 times the VDD. Now we know how to build a fixed oscillator, we understand, or a fixed frequency oscillator, and we understand what sets its amplitude. The next question is, how can we tune the oscillator? We know that the resonance frequency is set by capacitance and inductance, so if we can change capacitance, we will be able to change the frequency. In the past, in older processes, PN varactors were used quite a lot. However, PN varactors can forward bias, and in MOS processes, most of the time people tend to use MOS-based varactors, so I'm going to focus on those. We can have 2 choices. We can use an inversion mode varactor, or we can use an accumulation mode varactor. An inversion mode varactor here shown as a PMOS is nothing else than a PMOS transistor in which we connect the source and the drain together, and we get a 2-terminal device between gate and source at that point. If we make the gate voltage much smaller than the source voltage, then this if we make the gate voltage much smaller than the source voltage, then the PMOS transistor will form an inversion layers. Holes out of the source and drain will go under the plate, and we get a high capacitance inversion mode capacitance. If we now make the gate voltage larger than the source voltage, the structure would like to go into accumulation. However, it cannot do that because it doesn't have a source of electrons, and so it stays in depletion, and we get a small capacitance under this condition. So we see that we can switch with a voltage, we can switch the capacitance between a lower value and a higher value, and we get a good Cmin to Cmax ratio. In accumulation mode, we use a different structure. We start with a PMOS transistor, but we replace the P plus source and drain, which you see here, with an N plus implant. What happens then is that as we drive the structure with a large source voltage and a small gate voltage, there is no inversion charge source available. There are no source of holes available, and the structure actually stays in depletion. However, if we make the gate if we bias the gate at a high voltage and the source at a low voltage, then what will happen is that electrons from the source here, from this N plus, will now go under the gate and will create an accumulation layer, and we get again a high capacitance. So we can switch again between a Cmax and a Cmin value. In practice, when you use those varactors, you're going to see that the parasitics matter, and there are quite a few parasitics on the source side. So typically, you're going to take the gate side and attach that to the tank, whereas you keep the source side to attach the tune node to it, because it will load much less the tank at that point. Which varactor to use depends largely on a lot of aspects in your process. However, here I refer to a study done a few years ago studying the performance of oscillators which have been designed with the same tuning range, the same center frequency, targeting the same phase noise specification, and then comparing the current that you need in order to make these specifications. And you see that actually the accumulation mode varactors indeed give us the lowest power consumption, and they often are the preferred type of varactor to use. However, one thing to note is that in order to use them, they need to be specially modeled in your design kit because they're not a standard transistor type. Varactors very often are also put in the following configuration in combination with a series capacitor, maybe an MIM capacitor. And the reason to do this is because now we can both control the DC voltage on the gate side as well as on the drain side, on the source drain side of the varactor. This allows us to better make use of the tuning range of the varactor given the constraints on the supply voltage or the constraints on the, let's say, the tune voltage that we have available in our system. A disadvantage is that we need to insert a resistor here because we need to make sure that the signal does not get lost there. We need a high impedance here. This resistor can add noise, and that can reduce the performance of the system. Additionally, the tunability of this varactor will be smaller, so we'll end up with slightly larger area to make the same changeable capacitance. But an advantage is that the quality factor of this structure will actually be higher than the quality factor of the varactor, assuming that the quality factor of these metal-metal capacitors is higher, which is typically the case. Now, what is the amount of tuning range that we need? In a lot of wireless applications, you will need tuning ranges or frequency changes of 20 to 100 megahertz, whereas you're using carriers in the region of 1 to 5 gigahertz. That means that the tuning range in a percent-wise, in a relative manner, is about plus minus to plus 2.5%, which is relatively small. At the same time, we know that we face process variations. Process variations typically do not affect the inductor too much because the inductance is really set by the geometry of the structure, which is typically very well controlled. Capacitors are another matter, however, because in capacitors we easily see plus minus 20% of process variations. Since there is a square root dependence between capacitance and frequency, we actually find that results in plus minus 10% of frequency variations that we can expect due to process variations. So really the tunability of the VCO that we need is largely determined by overcoming PVT variations rather than the requirements of the application, but this is for narrowband wireless type of applications. Now, given this requirement, we can take a look at what the average tuning gain is that we will need from the VCO, and its dependence on the available voltage range as well as the center frequency. And we see that the VCO gain tends to go up as our VDD is coming down in nanometer processes. This is not a good thing because this will lead to larger spurs, reference spurs, and can also lead to more noise in the VCO. So generally what people try to do is to use a discrete tuning mechanism, basically a digital tuning mechanism. So instead of trying to cover here in this graph this frequency range we need with a continuous tuning characteristic shown in the background in gray, we make a number of overlapping tuning characteristics between which we switch by switching tuning elements, in particular either switching the inductor or the capacitor in the VCO. Switching inductors turns out to be not that easy. Most of the time people will use a set of multiple VCOs and switch between the VCOs. I'll show you also an example later. If we want to change the capacitor, we have two choices. We can either use switched capacitors or we can use switched varactors. The switch capacitors, there are a large number of different implementation styles, but here I show a differential switch capacitor for discrete tuning. So we take two capacitors and put a large NMOS transistor here in series. When the V control voltage goes high, this NMOS transistor will turn on, at least if we are sure that the source voltage of this NMOS transistor is sufficiently low. And to ensure that, we put two smaller transistors here that will make sure that in DC this voltage goes low and this NMOS transistor turns on very well. As soon as that happens, this R-on resistor is fairly small. This guarantees us that the quality factor of this capacitor when we put it in the tank is sufficiently high, and the differential capacitance turns out to be C/2. Now, when we turn this structure off, what happens is that, and unfortunately, well, it's not very good to see, but what happens is that we still remain, or we are left with the parasitics of the transistor. Overlap capacitance, diode capacitance, and what happens is that in order to make the on resistance small, we tend to use large devices, but they come with a lot of parasitics in the off state, so we have a trade-off here, and it turns out that the capacitance in the off state does not go to zero. Also, we have to also be careful about what the quality factor is going to be of this capacitance. This is hard to make general rules about this because this now all becomes very layout and process dependent. Here is an example of a VCO which I would say has an extreme tuning range. It has a tuning range of up to 1 gigahertz. The reference is provided here, and it's done with a set of binary switched capacitors. Now, when you change the capacitor over such a wide range, what is going to happen is that the characteristic impedance of the tank is going to change, and the amplitude of the oscillator is going to change. So in that case, for example, shown in this paper, you probably will have to adjust the current in order to make sure that the amplitude remains where you need it to drive the subsequent stages. An alternative to switched capacitors is to use switched varactors. I have an example here of an oscillator where the common mode voltage of the output signal sits around half supply voltage, which means that if we take the control voltage to a low value, that these PMOS varactors will go into depletion and will have a capacitance of about 20 femtofarad. On the other hand, when we take the control voltage to the VDD, they will go into inversion and they have about 90 femtofarad of capacitance. So we see a range of about a factor of about 4 between the minimum and the maximum capacitance in this example. And these capacitors are unit cells, and they need to be driven by a thermometer code. So you put in a little bit of logic, and then you can build up these tuning characteristics in which you can discretely tune between these continuously tunable characteristics. In all these designs, it's important to make sure that your analog tuning varactor is sufficiently large that it can always cover this frequency step that you incur when you switch in a minimum unit cell or a minimum cell in any of these switchable varactors, so that there are no holes in the frequency and the output frequency. One of the questions that very often occurs is what kind of oscillator topology should we, or arrangement should we use? On the left here, I have a tail-biased topology. We have discussed that already a couple of times. Basically, the signal, the common mode of the signal will sit around the power supply voltage. We can get very large swing out of this kind of oscillator. However, one important consideration is that the drain voltage on this side can go all the way to ground, while the gate voltage goes all the way to 2 times the supply, which means that the gate drain stress in this device can be quite substantial, and depending on what process you have, that can lead to reliability issues. Also, a high common mode level for the signal sometimes gives you reduced flexibility in getting a good tuning range out of your varactor. So we can switch to top bias topologies. In this case, we can keep the common mode of the signal around half of the supply and make sure that all the signal swings stay within the supply rails. Of course, now the signal swings are going to be smaller, which can have an effect on noise, but we have better reliability in many cases. Also, the tunability can get better because the common mode at half supply is often more compatible with the varactor biasing. Another alternative is to use complementary VCOs. They tend to give a larger amplitude for the same I bias, and at the same time, however, it's not always very clear if the PMOS transistors or the benefits that the PMOS transistors add is really beneficial in terms of the power-noise trade-off in oscillators, and that might also depend on specifics of your process. So at this point we have discussed, let's say, the wanted behavior of an oscillator. Now we have to start looking at some of the unwanted features, starting by the fact that there will be noise in the oscillator. Now, what is specific about oscillator design is that we are now dealing with circuit noise sources, voltage noise and current noise inside the circuit, but the quality of the signal that we expect is typically in terms of the phase of the signal. The amplitude noise is also present, but we'll see later that it typically gets suppressed, but phase noise is really what is the quality that we expect of the signal. Now, if we look at the real oscillator spectrum shown here on a spectrum analyzer, we see that indeed, due to phase noise, there is not just a single impulse of energy, of power, but the power is spread across, the energy is spread across a number of sidebands of the oscillator. We can then look in a more zoomed-in picture here of a phase noise, single sideband phase noise measurement, where we have here the power spectral density or the phase noise in a 1 Hertz band at a certain offset frequency here on the horizontal axis. For very close-in frequencies, we typically find that they're due to upconversion of 1/f noise, and that results in a slope of minus 30 dB per decade, whereas further out we find a slope of 20 dB per decade, because here the noise is due to noise, to circuit noise, which has a white noise spectrum. Phase noise analysis is quite involved, and there are actually two main ways to approach it. On the one hand, we can do a frequency domain type of analysis where we inject a noise tone into the oscillator, or to analyze it better, we have a noise tone into the oscillator. We see how it affects the sidebands of the oscillator and then decompose those into amplitude and phase noise contributions. Another approach is to use more of a time domain approach, where an impulse is injected into the oscillator at different times, and then it is studied what the effect of this impulse is, of this noise impulse, on phase shifts and amplitude shifts in the oscillator. And I'm going to go through this primarily in a qualitative manner. When we take a somewhat idealized oscillator shown here and we inject a noise pulse at different times, we can find two very different behaviors. On the one hand, if we inject a noise pulse when the oscillator has a maximum voltage, what we get now is that we're injecting a current with a certain amount of voltage across the current source, which means that the current that this noise source is injecting energy into the oscillator. So that indeed then translates to a larger amplitude of the oscillator, and in fact even turns out that there is no phase shift in the oscillator when the current pulse is injected at those time instants. However, when we inject the current at the zero crossing of the voltage, we basically did not inject any energy into the oscillator, which means that we cannot change its amplitude, and it turns out we can only move the waveform back and forth, or we basically only introduce phase shifts. So we see here that we have a system that, depending on when the current pulse is injected, we will get a different response. And here what we have then, or what can be defined, is an impulse sensitivity function, which gives us the amount of phase shift that will occur given for a unit impulse of current. And we see that this amount of phase shift will be maximum when we are at the zero crossing and will be minimum when we're at the top of the waveform or at the minimum of the waveform. Now, real oscillators have always an amplitude regulating mechanism. I showed it in the earlier one. There is a limited amount of current available that can be switched around. That determines what the amplitude can be. So there is always a amplitude regulating, implicit amplitude regulating mechanism, which means that if we start plotting the phase portrait of the oscillator, we find that there is one determined or one preferred limit cycle in this phase portrait. So here we have the voltage as well as the derivative of a voltage, and we plot the locus over time of these two variables. If we try to push the oscillator away with noise, we find that the amplitude changes are being suppressed, and they will fade away over time as shown here, whereas the phase shifts, the phase disturbances persist forever, because the oscillator itself has no idea of what phase it should be at. So if you move its phase, it cannot recover from such a disturbance. In fact, this is an ideal integrator because we apply an impulse and we get a step response here. So as far as noise analysis goes now, we have the following system. The noise impulses go into a linear time-varying system. It's a time-varying system because depending on the timing of the pulse, we will get a different phase step. And it is a linear, and it turns out to be a linear system. At the same time, then we can compute the corresponding phase of the oscillator given here. If we want to know what the output voltages of the oscillator, we have to go through a nonlinearity, basically the sinusoidal mapping. Now, at this point, we have determined that the relationship between the phase of the oscillator and the noise impulses can be modeled by this equation. We find that, as I mentioned before, we are dealing with an ideal integrator, and that there is a noise, an impulse sensitivity function that we need to take into account. Now, for most noise sources, we don't know much about their time domain properties. We typically know much more about their frequency domain properties. So what we want to do now is we have a power spectral density for the noise in the frequency domain, and we want to find out what the power spectral density is of the phase. When we look into detail, and I think Professor Razavi also went over this to some extent, but what we see is that two things will happen: a frequency translation. So there are frequency folding effects that can happen depending on the harmonic contents of this impulse sensitivity function. And additionally, because we are dealing with an ideal integrator, we get an integration of the noise. So white noise becomes a random walk and gets a 1 over f squared dependence once we look at the power spectral density of the phase. Once we have the power spectral density of the phase, we can go and look at what the power spectral density of the output signal becomes. And it turns out that to the first order, it's primarily an upconversion of that noise spectrum for many practical purposes. So if we go through the analysis, we can find that for a white noise source, the following dependence exists between the phase noise and then the noise power spectral density, as well as some other properties of the oscillator, like the gamma RMS, or the voltage and the capacitance. We can plug in the amplitude, which we know from the current limited regime equation, and then we come up with the following equation that I'll discuss also in the next slide. Two more remarks to make is that each noise source has its own ISF. It's not true that all noise sources have the same ISF. We need to very, very carefully model the specific ISF for each noise source. And secondly, there is another complication that the noise sources typically are cyclostationary, because the devices change widely between different operating regions, and we can accommodate that by using an effective ISF. So far we have determined that the output noise now for a white noise source is given by this expression. And as designers, we want to find out what are the parameters that we can change in order to improve the phase noise of our circuit, and what are the trade-offs in performance that we face. Well, a lot of those can be derived from this expression. First of all, we notice that in order to achieve the same phase noise at a given offset frequency, that this will become progressively harder as we have higher and higher center frequency of the oscillator. That's just an intrinsic property, and that's not something we can do much about. Secondly, we see that in order to reduce the phase noise, we will need to increase the signal, and the denominator of this fraction, which is proportional to the signal. And there are two ways to do it. First of all, we want to have as large a Q as possible. To a large extent, this might not be under our control because it's determined by the technology. But definitely, if we have any choice available, we should always try to get as good a Q as possible. Secondly, we can improve the phase noise by increasing the bias current. Now, this of course comes at the price of more power consumption. We have to be careful we don't get a quadratic improvement, because as we increase the bias current, this term, the power spectral density of the noise, will typically increase as well. And so in most cases, we just have a linear dependence between the phase noise and the power consumption. So all these things then, if we are interested to really see what the qualities of our design compared to other oscillators design, we want to take out the first order trade-offs that are intrinsic, the power trade-off as well as the frequency trade-off. And so we can then normalize our phase noise performance, for example, compare with its power consumption as well as its center frequency, and compare different oscillators based on their figure of merit. This primarily, or actually only applies in the 1 over f squared phase noise region, which is important to remember when you make the comparison. Now, a couple of words about inductor Q and actually how that impacts the, the trade-off between area and phase noise in many on-chip oscillators. If you give me a lot of area and I need to realize a certain inductance, what I can probably do is just make one big wire and just a single loop to achieve that particular inductance. It turns out that those inductors in most processes have the highest possible quality factor that you can make in the process. If, however, you restrict me to a smaller area, I'm going to have to use thinner wires, coil them up more, and I'm going to incur a number of more significant resistive losses, also current crowded losses, and so forth. To the first order, actually, you can show that the quality factor of the inductor is proportional to the square root of the area that you have available to build it. Now, since the phase noise is proportional to 1 over the square of the quality factor, we actually can claim that to the first order there is a 1 over that the phase noise performance of the oscillator is inversely proportional to the area that you have available. This is, of course, under the assumption that the inductor is dominating the quality factor of the tank. In that case, we can, if we want to compare oscillators or if we want to get an estimate of what performance we can expect, we can use an area normalization in the FOM, and that is given here in this expression. Now, beyond area and power, we can also try, maybe let me go back, we can also try to change this term in the equation. The gamma effective RMS has something to do with how the circuit noise sources inside the oscillator are translated into phase noise. And if we understand this well by using these analysis techniques that I mentioned, we can maybe come up with topologies of oscillators that are less sensitive to phase noise than others. One such example is given here. In this paper, it was analyzed and determined, and also in other papers, that the noise of the current source has different effects depending on the spectrum or the parts of the spectrum of this noise. So if we look at the low frequency components in this noise, they get upconverted around the carrier, but they primarily contribute to AM sidebands. They primarily result in amplitude noise. Whereas the noise of this current source here that sits at twice the frequency, it gets down converted around the carrier and results both in AM and PM AM and PM modulation. So if we know this, we can actually realize that by putting a low-pass filter here, we can avoid the high-frequency noise to get into the oscillator, but rather be shunted into this capacitor. And as a result, we can indeed see that a phase noise improvement can be obtained. In this particular work, they obtained 7 dB of noise of phase noise improvement. Now, of course, the price that you have to pay is this additional filter shown here in the box that you need to insert on the die, and that, of course, has a quite significant area. In this example, it's almost the same size as the resonator. An alternative to try to reduce the noise of the oscillator is to create a to inject only energy into the resonator when the voltage across the resonator is maximum. We remember from a few slides ago that at that point the sensitivity to phase noise or the resulting phase noise will be minimum. This basically means that we need to create a tail current source that will be maximum when the voltage on the oscillator is maximum, and that will be zero when the voltage on the oscillator goes through a zero crossing. You can actually show that by putting a capacitor here in parallel with this current source and relying on the second harmonic content that is always present in the common source node, that a second harmonic current can be created here that when it's summed to the constant current here, sets up a shaped tail current that exactly achieves this waveform. So what happens now is that these transistors only inject energy into the tank when the voltage is maximum, and we will actually get a much better energy or a much better conversion of the energy into amplitude of the oscillator. So indeed, if we build two of those oscillators, we compare them. One has the extra capacitor and the other one does not. Then we see that we get a larger amplitude out of the tail current-shaped oscillator. Both are operating with the same power. And at the same time, we also get a lower phase noise. In this example, was about 3 to 5 dB. We notice that in this case, the area overhead of this technique is, of course, much smaller. Finally, one last example, more recent example, is a Class C oscillator. It operates along a similar idea where you want to create waveforms going into the tank that are impulsive and only are non-zero when the tank voltage is at one of its maxima. This can be done in this case again by using a tail capacitor, but additionally a level shift is introduced in the gate, and you need to apply some capacitive coupling here. And this can give a very good, very low noise of the oscillator. And this oscillator probably still is the best reported FOM in the literature. One tricky part, however, is that, as you can see here, the noise does depend quite substantially on the value of this bias voltage. So generating this bias voltage reliably is somewhat of an issue, as well as possible startup issues for this particular oscillator. Okay, so now we want to go further and look at some more unintended properties of oscillators that will affect their performance. The first one is that oscillators are not only tuned by the tune node, but most oscillators are also being tuned by the supply voltage. In this particular example, the supply voltage sets the common mode of the signal, and if we keep the tune voltage constant and change the supply voltage, then the voltage across the varactor will change, and as a result, the frequency of the oscillator will change. This means that if we have interference on the power supply, that it will be converted into phase noise, or it will have FM effects and it will be converted into phase noise. Similarly, actually, you can show that any amplitude noise that exists on the waveform through the varactors can also be converted back into phase noise, and that can be a significant concern. Even if you design your varactors well, there is a reference here to a paper that gives some guidelines how to reduce this effect. You actually find that ultimately you're limited by the parasitic varactors that exist in the circuit, for example, the diodes associated with these transistors, the variable gate capacitance associated with the negative resistant transistors. So in many oscillators, especially if you have to put them on an SOC, you will need to use a supply regulator in order to make sure that they can meet the performance while the unregulated supply can have a lot of noise. So in this case, however, also I use this as an example where if we have a supply regulator, you could argue that maybe I don't need the current source in the tail, and I'm just going to rely on the supply regulator in order to keep to control the oscillator and give it a good PSRR. Indeed, when you have a structure like this, an oscillator like this will always operate in a voltage-limited regime. The amplitude will be set by whatever VDD you have. In practical cases, you probably want to make sure that the regulator is also controlled by an amplitude detect circuit to make sure that the oscillator operates reliably. The removal of the current source tends to take out some of the flicker noise sources that come out of the current source. And one of the challenges, however, is that in order to create a good regulator, of course, we need to use quite some power in the series regulator. In one instance that I want to point to here, some people have come up with ideas where you try to reuse that power by merging the regulator circuit and the oscillator circuit together, but I point you to the reference. It would lead us a little bit too far. Okay. I said I would spend a little bit of time on buffers. Actually, to illustrate the issues with buffers, I took an extreme example of a buffering challenge. In this case, we're looking at a PLL which has a 4 to 8 gigahertz range, and it needs 4 VCOs in order to cover this range. So now we are faced with a challenge that we have 4 VCOs here in this schematic. They are layered on top of each other, which we need to be able to switch between each of those VCOs on a common bus, and then that will then drive the feedback divider.
The way it was done in this particular example is after the VCO, a buffer was used and then a V2I converter, and all the VCOs were then, or all these V2I converters were wired together on a common bus. Now you have to realize that these VCOs are quite large and that this common bus, of course, also becomes quite large, so there is a lot of parasitics involved here. In this particular paper, a active inductor was then used in order to resonate out some of these parasitics. By using an active inductor, the area penalty was much lower. And after this stage, then a amplifier drives better the programmable divider. Another point to note from this example is that I already pointed out that within a VCO you need to make sure that the different tuning characteristics have sufficient overlap. Here shown are the tuning characteristics of the different VCOs in different colors, and you see that again, to guarantee that there are no holes in the spectrum, you always need to make sure there is sufficient overlap between the different VCO tuning ranges. A few words on nanometer challenges. As I pointed out in the beginning, we are actually stuck with LC oscillators, it looks like, when we need high performance oscillators. So whereas in a lot of circuitry that you see in nanometer CMOS technologies, inductors are being eliminated because the transistors have high FT, what we find is that for oscillators, we are stuck with this one inductor to create a good resonator. Now the question, of course, comes about if we could use the higher FT of the process to reduce the size of the oscillator. What is shown here is an attempt at doing this. So we start, let's say, with an oscillator at a given frequency of 0, and it has a particular size d. And now we look at what happens to the inductor when we scale the inductor to a size d by 8. The area of that inductor will now be 60 times 4 smaller, 60 times smaller. The inductance is 8 times smaller, and interestingly enough, if you look at 8 times the frequency of the original design, you find that you have the same quality factor for the inductor. Now, given that we have high FT in the transistors, we can exploit this to build faster oscillators than we really need. So what we are comparing here is a set of oscillators with using these inductors of the previous slide. So for example, we have a 1 gigahertz oscillator, it's hidden a little bit here, with a big inductor, and we compare it to an 8 gigahertz oscillator with a smaller inductor, all operating with the same power budget. What we see then is that all these oscillator designs turn out to have the same figure of merit. This implies that if I take the 8 gigahertz oscillator signal and I divide it by 8, that I get a signal with the same phase noise quality as I get out of the 1 gigahertz oscillator. So what we have here is an opportunity to indeed use the FT of the process in order to build a higher frequency oscillator that we need, which has a smaller area. Of course, implied is that the power consumption of these dividers needs to be sufficiently small compared to the oscillator power so that it doesn't dominate the problem, but in many practical cases that actually turns out to be the case. And it then offers us the opportunity to have very substantial area scaling, which then manifests itself if we start plotting the figure of merit normalized by area of all these different oscillator designs. Okay. So at this point, we finished voltage-controlled oscillators, and we're going to look at how to design programmable dividers. The basic function of a programmable divider is to take n input edges and at the output give one output edge. The basic implementation of this circuit could be a synchronous counter. The problem when we would use synchronous counters for frequency synthesis applications is that they are too slow for the type of frequencies we want to achieve. I think this was already shown in an earlier talk, but a typical solution to that is to use a dual modulus prescaler in combination with 2 synchronous counters. For now, if we ignore the presence of the swallow counter and we assume that this prescaler is dividing by n, then we realize that the division between the input and the output will be given by n times p. If we now look at the presence of the swallow counter, what the swallow counter will do is that for s cycles out of the p cycles, it will actually force the dual modulus prescaler to divide by n plus 1. So since we do this for S cycles, it results in swallowing S additional cycles of the input frequency, and so we get a division ratio which is now P times N plus S. With the appropriate choices of P, S, and N, we can actually cover typically the numbers we need in terms of what the specifications are for the divider ratio. For these dual modulus prescalers, typical numbers are 4, 5. I think in an earlier presentation, an example was given by 4, 5. You find 6, 7, 10, 11, 16, 17, and many more. In fact, the example I'm going to show here is a 2-3 divider example because it also, we will need it later for later architectures. Now, one thing to point out, let me maybe go back one slide. The advantage here is that we now, these synchronous counters operate on average on a much lower frequency, and so overall, if we can design this as operating at fast frequencies, then we can reach higher operating frequencies than we can reach with the regular synchronous counters. Okay, let's quickly look at how this 2-3 circuit works. So if the modulus control is put to 0, then you can easily figure out that this signal will go to 1, which means that this AND gate becomes transparent. Latch 1 and latch 2 now are configured as a master-slave flip-flop, which we drive with the input signal, and you know when you feed it back onto itself that at the output you're going to get half of the frequency. So we get a divide by 2 function when the modulus control is 0. When we put the modulus control to 1, then latch 4 and 3 also make a master-slave flip-flop, and they participate in the operation of the circuit. In fact, now we have a circuit that can have 4 states, but the AND logic here makes sure that only 3 of the states are allowed, or we cycle to 3 of those states driven here by the input frequency. So in effect, we have a divide by 3 circuit. There are many more examples of these type of circuits in the slides before and also in Professor Azavi's book. An alternative to using these kind of architectures is to use phase shift multimodulus prescalers. Let me explain briefly how they work. So also here we start with a master-slave flip-flop, which we feed back onto itself. So the input frequency goes in and comes out at half the rate with a phase shift of 0 and 180 degrees. Now we repeat this, so we have 2 more flip-flops. Now we get a signal here at a quarter of the rate, and if you go through the diagram here, you will see that you get a phase of 0, 180, 90, and 270. If we for now ignore the mux, we go from Fin to Fin over 4, then we divide by N, so the output frequency is going to be 1 over 4 times N of the input frequency. Now, if we look at what the role of this mux is, we have to look at the diagram down here. So if there is no switch signal, if we keep this mux in a fixed connection, that means that, for example, we're using the P0 waveform to drive the divide by N, then we see that 4 cycles are absorbed between the input and the Q signal, and we divide by 4N. Then for 1 cycle here, what happened is that there is a switch signal impulse coming in, and what it forces the mux to do is to switch at this point between the P0 waveform and the P90 waveform. What this does is it delays this falling edge by exactly 1 cycle of the input frequency. So that means actually that now there are 5 cycles between this rising edge and this rising edge. So we divided by 5, or we basically swallowed 1 additional input cycle for every switch signal here. You can see the same here. So that means that if we do k pulses, that we will swallow an additional k input cycles, and that we divide by 4n plus k. Now, what's the advantage of this structure? It is that we have an open loop system here from this point all the way to divide by 4. We just need some master-slave flip-flops. They can operate at very high speeds, and then we just need to mux between these waveforms at this point. The main design challenge in this type of divider is that we need to properly align these switch control signals with the waveforms, because if they come in the wrong times, we can have all kinds of glitch problems. But several solutions for this are available from the literature. I've provided the references here. Finally, a third divider topology that you can consider is what is called a truly modular programmable divider, which is built up from these 2-3 divider cells. So we make a cascade of these cells, and we also make sure that there is a control path that connects all these cells together. The basic operation is as follows. If for now we ignore that there is any additional control signal, then we see that between the input and the output we will divide by 2 to the n. However, if you analyze the operation of the module of this control path, what will happen is that for every output signal, a modulus control signal will ripple through the divider. Whenever it arrives, for example, at this 2,3 cell, what it will do is that for one of the cycles of the 2,3 cell, depending on the value of P0, the 2,3 cell will divide by 2 or by 3. So if the P0 bit is set high and the modulus control signal arrives, this cell will divide for one of its cycles by 3, which corresponds to swallowing one of the input cycles of the signal. Now, at this point, the input frequency is half, so if we swallow a cycle here, it corresponds to 2 input cycles of the input, and so on. So we see that depending on the setting of these p bits, that the divider ratio now will be 2 to the n plus the number of cycles we swallow, which is nothing else than p0 plus 2 times p1 and so on. So with this kind of an arrangement, we can actually divide by 2 to the n to 2 to the n plus 1 minus 1. So for example, 64 to 127, 128 to 255, and so on. Now this is not always very convenient. This can be quite restrictive. However, you will appreciate that with some additional logic, which primarily will operate at the end here, we can easily make a divider which has a variable length, and so then the n can change and we can cover a large range of divider ratios. The implementation of the circuit is shown here. We already discussed it earlier on. So now we so far have talked about dividers at a logic level. The question now is, how are we going to go down to the transistor level? We have two choices. We can go with single-ended type of circuits, rail-to-rail signals. We can use through single-phase clock logic. We can use C-squared MOS logic. Or we can use more of a source-coupled logic type, which operates differentially with smaller swings and generally operates with higher speed. In fact, if we choose this type of logic, the presence of these current sources here and appropriate biasing circuits really make this choice of a latch the most robust against PVT variations. This instantiation doesn't have the current sources, can have a larger headroom, needs less headroom, but it's typically more susceptible to PVT variations. Next, I want to go through an example of a divider design to just look at the whole architecture and the implementation. So the first challenge is that we typically need not just D latches, but we also want to have an AND logic in front of it. But fortunately, it turns out that you can absorb this logic into the structure here so that no additional delay is incurred by implementing this additional gate. And this means that we can operate the circuit faster. Okay, so let's take a look here at a divider example. This was a very low voltage design. It operated from 650 millivolt supply. It operated in the 2.4 gigahertz band. The frequency at its input is 2.4 gigahertz, and at the output we want to go to a reference of 16 megahertz. We have 4 stages of source-coupled logic, and then at this stage we have a frequency which is in the range of 140 to 160 megahertz, and at that point we go to regular CMOS divider logic. So what we see here is indeed we have this cascade of 2-3 cells. They're implemented with this type of logic, but with a source-coupled design style. And one thing to note here is that as we go through this divider chain is that the frequency becomes progressively smaller. So in theory, since the frequency about halves, we could in principle scale the power by a factor of 2, although in practice typically you do a less aggressive scaling because you also to have a sufficient margin. The next thing then is to look at the CMOS divider implementation. This can be done typically with standard logic cells because the frequency came down substantially here. And also what is shown here is this modulo extension logic, or at least a block diagram of it, and you will see that it basically gives you the ability to change the length of the 2-3 divider change, and then you tap off the appropriate signals to go to the output. Last thing to point out here is the resynchronizing flip-flop. We'll talk about it more later, but I want to show you that it's here and it's connected to a clean edge of the VCO and retimes the output of the divider. Now, how do we implement, for example, these short coupled logic, these source coupled latches at very low voltages? This example operates with 650 millivolts. The common mode here is 500 millivolts. This common mode sets then the common mode on the D and the clock inputs because these dividers are driven with signals from similar circuits. And in order to then bias all these transistors in the appropriate region, you can easily derive that you want a common source here of about 300 millivolt and a common source at this point of about 200 millivolts. That actually means that you should have the ability to change the VT of this transistor as well as the VT of this transistor. And it turns out that in deep submicron, indeed, or in nanoscale CMOS, indeed, the transistors have a strong dependence of their threshold voltage on their length. So we can use a somewhat longer transistor here for M1, get a lower threshold voltage, and one also operates at a lower speed because it's on the D input. And then we can use a somewhat shorter transistor for M2. It has a higher threshold voltage, but we can accommodate that in the biasing. And then additionally, we can apply some forward body bias to further tune the VT to the value that we need. One last remark here is about the necessity of doing output synchronization for dividers. Here is an example, it's in a somewhat older technology, but of a study comparing dividers with a synchronizing flip-flop on the bottom and without a synchronizing flip-flop. You notice that the synchronized divider has a much lower noise than the non-synchronized divider. And as already mentioned in earlier talks, this is common practice that a synchronizing flip-flop is put at the output, because also what it results in is that the divider design now can completely focus on speed, on low power consumption, robustness, and the noise of the divider does really not contribute significantly. The noise contribution or the noise properties are completely determined by this flip-flop design, and it's very well concentrated in this one circuit. I'm not going to spend a lot of time here. This is for completeness and for your reference. If you need to build very high frequency dividers, for example, if you want to design millimeter wave PLLs, you will probably use this type of Miller dividers, but they have a fixed divider ratio. They're basically a fixed prescaler which you can incorporate in your loop. Okay, so we're going around the loop and we have arrived at the phase frequency detector now. Phase frequency detectors actually have been extensively discussed by the previous talks. In some applications, but typically not very much, only in high frequencies, maybe XOR or multiplier phase detectors can be used. But most of the time we will use a phase frequency detector, which is shown here. Its operation has been explained multiple times, but the basic idea is that the reference pulse will activate the up signal, the voltage pulse, the VCO pulse will activate the down signal. The two signals overlap for a certain amount, which is set by the delay here in the feedback path, but when both are high, a reset is generated and the two signals go back to down state. The advantage of this detector is that if we look for very large phase errors, which will occur when actually the frequency of the two signals are not the same, the phase error can keep building up and go beyond 2 pi. In this case, we see that the sign of the signal always stays the same and that we will now have an automatic frequency acquisition built into the PLL. We need to avoid the dead zone, and that is done by this additional delay. One thing to point out about this delay, beyond all the other things that people have pointed out about it, is that it will also set a it will also mean that while these two signals are high, you cannot process any new incoming edges, so that will set a limit on the speed of the phase frequency detector if you make this delay too large. Why we need this extra delay is also briefly explained here, but it was already explained at length, that it would result in a phase into a dead zone if we don't apply the delay, so I'm actually going to skip over this. How do we go now into the circuit level? Well, here is just a gate representation. There are many different possibilities. This is just an example. This is relatively straightforward. Really, the design issues are at what is now the performance of this phase frequency detector. So we need to figure out what is the noise contribution of the phase frequency detector and how does it relate again to the transistor noise sources in the circuit. This is actually quite a tricky problem, but let me try to give you some qualitative explanation of how we go about analyzing this. So these are logic circuits that we are dealing with, and they will make a transition, as shown in black is the ideal transition, but in reality there will be noise on these, at the output of these circuits, and that noise will add to the real signal, and the zero crossing of the transition will be modulated or pushed around by that noise. Now, if we know this noise, the RMS voltage of this noise voltage, the RMS value better of this noise voltage, it's relatively easy to show that if we know the slope of the signal, that the corresponding timing jitter is then given by this expression. As I put it here, this is really the easy part. The hard part, or part of the hard part, is to figure out when you have the circuit noise sources inside the circuit, how much RMS noise that will result in the output of the signal, in the output of, or in the inside the circuit. I point you here to two papers that can get you started with this type of analysis. The other thing to note here is that obviously what we want to do is to make the slope of the signal as high as possible so that the amount of, if we can keep the voltage noise constant and increase the slope of the signal, then we will get less timing jitter. Now, at this point, we found that there is a certain amount of timing jitter that occurs in this circuit, but we want to really find out what the power spectral density is of the equivalent phase noise that is being added by this phase frequency detector. So we still have some analysis to do. The first step is to go from timing jitter to the phase jitter. Again, this is relatively easy because we know that a given time shift, if we have a given time shift and we multiply it with 2 pi and the reference frequency, that we can find out what the corresponding phase shift is. So we can also apply this to the phase, we can also compute the phase jitter given the timing jitter here. Still, at this point, we have the RMS value of the phase noise of the divider, and what we really want to find is its power spectral density. Now, as already mentioned in earlier talks, the phase frequency detector is really a sample data system, and it's a little bit involved to then go from one to the other, but generally the assumption is made that the phase noise of the PFD is white, its noise bandwidth is FRF over 2, and if we can make that assumption, we can relatively easily find out what the power spectral density of the noise is given the timing jitter that we calculated on the previous slide, and we find this dependency here on the reference frequency. Now, once we know the S phi at the input, we want to know how it affects the output phase noise, and then we realize that we just need to multiply it with the gain of the PLL if we're looking inside the PLL bandwidth where this matters. And we then find that the phase noise will depend on the properties of the phase frequency detector as well as on the N factor or the reference frequency. Now, if you think about it, if you design a PLL, typically you're given the output frequency. Sometimes you're also given the reference frequency. Maybe you can choose it. But so this version of the equation is really gives us a little bit more insight. What we see from there is that if you have the choice to change the reference frequency, you should make it as high as possible, at least in terms of reducing the contribution of the phase frequency detector noise. If we want to compare different phase frequency detectors, we typically use this kind of a figure of merit because it's independent of the particular frequencies in the PLL. This then gives us the phase frequency detector figure of merit, which in the current state of the art is in the order of -210 to -220 dBc per hertz squared. There is a square missing here. This can actually improve. This is a very recent result. Also this year at the conference there were some improvements on this idea, but the idea is to use subsampling phase detectors, and it can be shown that they can give you a very good phase frequency detector behavior. The basic idea is to sample the VCO signal, which comes in from here, on a positive edge, for example, of the reference. And then we get the waveforms shown in red and green are shown here. And so we basically get a sample of the VCO output signal. You can fairly easily show that the corresponding phase detector characteristic is a sinusoid, and the gain or the slope of this characteristic is very large, which is good because that means that the loop will have a very large, very high phase detector gain, which is beneficial to reduce the noise of other components except for the phase detector. Then in order to control or to derive the necessary control signal that needs to go into the loop filter, what is done here is to introduce a pulsar signal so that narrow pulses can be created, which are then integrated onto the loop filter, and what you see here then is the resulting PLL circuit that is using this subsampling phase detector. One thing to note is that this loop has a very, very narrow locking range, and you really need to engage an additional frequency locked loop which has a dead zone in order to make sure that you pull the VCO first to the right, close to the right position, and then when you're sufficiently close, this high performance loop will take over. One thing to note is that this architecture is only working for integer and applications, but it gives you a very good performance. It improved the state of the art by about 15 dB. If I remember correctly, the phase detector quality factor is minus 235 dBc per hertz squared. Okay. So we're coming out of the phase detector. We have our up and down pulses. We now need to transform them into currents that we can integrate on the loop filter. So we need to design a charge pump. Shown here is a very basic charge pump. For example, this charge pump is using source side switching. So when the down signal goes high, what we set up here is a current mirror between this transistor and this transistor. A down current will be pulled out of the filter, and charge will be pulled from the filter. Similarly, there is actually a mistake here. There needs to be a complement here. When the up signal goes active low, a current will be pushed into the loop filter, and so we can transform, or we can convert the up and down signals now into charge packets that we dump onto the filter. As already mentioned several times, there are several design challenges with this type of circuit. A first consideration is that we would like to have as large headroom as possible so that we can get a good swing on the VCO tune voltage so that the key VCO can be reduced. Additionally, we face a matching. If there is mismatch between in this current mirror or mismatch in this current mirror, this will result in different up and down currents, and as explained in earlier lectures, this will result in a static phase error and consequently also reference spurs. Additionally, due to channel length modulation, what can happen is that as this tune voltage starts to change, this down current will change and will not match exactly anymore the up current that comes out of the PMOS. Again, we turn up and down current always on together for a certain amount of time, which was a delay in the feedback of the phase frequency detector, and during that time that error will be integrated onto the loop filter, and the PLL will have to respond by again inserting a DC phase offset at the input. Now, there are a number of ways to overcome this. One example that I think was also discussed earlier is to make sure that if this voltage starts to change, to copy it over with an error amplifier and to change accordingly the reference for the PMOS current mirror, so that now the PMOS current always matches the NMOS current, or the up current always matches the down current. So important to remark is that the down current will still change with the tune voltage, but the up current will match those changes so that we don't have a problem as far as reference spurs is concerned. A similar idea is shown here. To reason, however, to show this is that this is a charge pump that is using gate side switching. The advantage of that is that it might give you a little bit better headroom. Additionally, you can typically switch these transistors much quicker, which might enable you to reduce the T-on time that you need, the overlap time that you need in the up and down pulses, and to reduce the charge pump noise to some extent. You notice that also here an error amplifier is engaged to get rid of the channel length modulation. Finally, here is an example of a charge pump that addresses both the mismatch as well as the channel length modulation. All the previous circuits were addressing channel length modulation but could not address the mismatch that would exist due to transistor mismatch in the current mirrors. This structure, on the contrary, what happens is the up current can be sent into the tune node or into the filter. The down current can be pulled out of it. But when we don't send it into the loop filter, it is sent into a dump capacitor on the side here. Now, if the up and down current, for example, are not well matched, what will happen is that the error will be integrated on this capacitor. This will be sensed by this V2I converter, and it will adjust the current in such a way that either the up current or the down current is adjusted, that the currents match to each other. Additionally, the reference of this V2I converter or of this feedback loop looks at this voltage here, this sense voltage, which then makes sure that the channeling modulation is also compensated for at the same time. So this solution now allows you to both take care of channeling modulation as well as device mismatch, because what you're doing is you're measuring the actual currents that go into the charge, into the loop filter when you don't need them. Now, a couple of practical examples. So first of all, in many charge pumps, you will find that they're built up of a number of parallel branches. In many cases, you want to have the ability to change the charge pump current so that when, for example, as you change the N factor in your PLL, or as you start changing frequency and the KVCO gain changes, you can actually compensate it maybe by changing the charge pump current to some extent. Additionally, what is shown here is a polarity switch between the up and down pulses of the phase frequency detector and then going into the charge pump. This, for example, is practical if you have off-chip VCOs and you don't know beforehand if they will have positive or negative gain dependence or frequency voltage dependencies. Yeah, that's. Or if you design your loop and you want to have the flexibility to switch the gain around, you can use something like this. Finally, a few words about charge pump noise and how we size the transistors to reduce the noise. Now, this here is for the case of integer N PLLs, where eventually the reference and the VCO will lock to a close to zero phase error. The up and down signal then will go on for a particular time, and when these two currents are on, the currents are shunted through the transistors. However, the noise will come out and will go into the loop filter. The noise can be calculated as the sum of the two noises, at least during the time that these two current sources are on. And the noise then is nothing else than 4kT times gamma times the GM of the transistor, and that can be rewritten as 4kT, the current, times gamma times the GM over I. The current typically is fixed, so what we can do as designers is to try to make the GM over I of the sources as small as possible. This means to use a large VGS minus VT, and of course that comes at the penalty that now we will need more headroom across the transistors, and that's the penalty you pay. Now, there is also another important issue here. This noise is a non-stationary noise, it's cyclostationary noise. And if we would like to analyze this, so these expressions here are only valid when the current sources are on. Now, fortunately, as already pointed out in the previous talks, the dynamics of the PLL are much slower than the reference frequency, so we can actually get away by averaging this noise, and the power spectral density of this noise then can be written as the ratio of T on times Tref times the noise that you have when both are on. This is an approximation, but it holds well enough, like all the other approximations that have been made in the PLL analysis. Another detail to note is that this is a double-sided power spectral density. If you calculate the phase noise, very often, I mean, you're working with single-sided power spectral density, so very often you'll find a factor of 1/2 that is needed somewhere. Okay. At this point, we reach the node in the PLL where we need a loop filter. So let's take a look at designing loop filters. So the most basic passive loop filter is shown here for a type 2 fourth order PLL. Its transfer function was shown before, but it's repeated here. It consists of three main sections. The dominant section here is the combination of a series resistor and capacitor. This gives us an integrating capacitor as well as creates a zero in the transfer function in order to make sure that we can make a stable PLL or a stable type 2 PLL. Additionally, very often you will find an additional capacitor C1 here, because at high frequencies this becomes high impedant because of the presence of this resistance here, and so reference spurs or delta sigma quantization noise would not be sufficiently attenuated unless we put this C1 here, and that then introduces an additional pole in the transfer function. Very often an additional filter, low-pass filter, is introduced to further filter the reference spurs as well as the quantization noise. I have some component values here for a particular example, but what I want to point out is the relative sizes of these components. These capacitors tend to be the largest capacitors, the other ones are then significantly smaller, and so when we think about integrating the loop filter, really the size of the C2 capacitor is what can be the most problematic factor. For that, in some cases, people try to use active techniques in order to reduce the capacitor size. I have two examples here. The top example is a dual path loop filter. So what you do is you split the charge pump output, you make two versions of the output, and you have an integrating path here with an active integrator, and then you have an RC path here in which you also insert a charge pump current. If we look at the frequency response of each of these paths, we have an integrator here, and here we have a low pass response. If then we sum the two voltages here, we obtain the following characteristic. And what is interesting to note here is that the position of this zero can now be manipulated by changing the ratio between this charge pump current and this charge pump current. By putting in more charge pump current on this side, we can push the zero to lower frequencies, which effectively comes down to using a larger capacitor. Then an additional filter section can be added here at the output. Of course, the price we pay is that we inject more noise into the circuit, and so there is a trade-off here between noise and area. A similar trade-off exists in the following active capacitance multiplication circuit. The basic idea there is to take a capacitor, measure the current through the capacitor, and then use a current-controlled current source to multiply that current, so that effectively we see a much larger capacitor looking into this. This can be implemented with a current mirror arrangement. Now, of course, the result is that additional frequency poles will be introduced. So you have to be very careful how they might affect the frequency response or the settling response also of your PLL. And additionally, we are replacing passive components, noiseless components, with active noisy components. So there is again a noise penalty to be paid. Another issue in integrating loop filters is that we will typically try to use MOS capacitors to build these big capacitors because they give us the highest capacitance density. Now, the capacitance is proportional to the area of the device, but also the gate leakage will be proportional to the area of the device. In fact, the leakage to capacitance is a technology constant. Now, I simplified the loop filter a little bit here. We have a big capacitor here with a substantial leakage current, and then we have a smaller capacitor here with a smaller leakage current. I should note that the component values have been modified a little bit to make this more pronounced in the simulation on the next slide. But basically what's happening is that due to the leakage, at a steady rate we lose charge to ground here, and we see that the sum of the two leakages comes out at the ground terminal. Of course, to maintain a steady state in this system, the charge pump is going to have to inject the necessary charge to replenish these capacitors, but the charge pump can only do this with very short pulse type signals. But on average, they will compensate the leakage current that droops away over here. Now, the problem with the fact that this is so impulsive is that these impulses will not go into this branch, but would rather choose to go into this capacitive branch. And moreover, the size of these impulses is, however, set by leakage that is set by a much larger capacitor than the filtering capacitor that we will have available to filter these pulses here. and that's then also evident from this simulation. So if we look at the right here, we see the charge pump current pulses going into the loop filter. Most of these pulses end up into the smaller capacitor, and then at a slower pace, the C2 capacitor is also replenished. But if we look now at the voltage disturbances, we see that the voltage, the tune voltage, which is the voltage across C1, has a much larger ripple than the voltage across C2, which is that internal node. So again, the challenge is that the leakage is dominated by the biggest capacitor, but the filtering that we have available only comes from the smallest capacitor. So you will find, also in previous years in ISSCC that people come up with a number of leakage compensation techniques to try to get rid of this leakage current. At this point, I would like to quickly review some of the challenges of PLL scaling as far as area goes. So you're familiar with the block diagram of a PLL, and against the blue background here, I have all the components that are primarily active circuits, and so we know that those will scale very well with technology. The oscillator is large, but we know that if we move it to higher frequencies, we can at least reduce its size somewhat. And so what we're still stuck with is these large capacitors in the loop filter that we would like to integrate on the chip without blowing up the area of the chip too much. One of the opportunities that exist is to try to reuse the area that we have under the inductor. As mentioned already before, in better low noise or high performance and thus low noise applications, we need to use an inductor in the oscillator. So we might as well try to make the best of it and reuse the area under the inductor. And in this example, what was done is to create a capacitor under the inductor that we can then use in the loop filter. So this is a MOS capacitor. It's laid out very carefully such that no eddy current paths can exist under the inductor. And indeed, we see that in the simulation of the quality factor that the structure does not see any degradation of its quality factor. In this case, actually, there's a slight improvement because this acts as a shield for the electrical losses. Once we have that, we can take the large loop filter capacitor C2 and slide it under the inductor, and now we get a very compact PLL design. In fact, what you notice is that the PLL area is really dominated by the oscillator. Here is the tank, and then here is the inductor, and then here are the variable capacitors that need to be contacted with a thick wire as well. The remainder of the PLL really takes a very small area and could probably even be laid out denser than in this example, and so we end up with a PLL that is very, very small, 150 micron by 283 micron. Also, at this point, a short summary about reference spurs and then some of the mechanisms that we need to watch out that go beyond what we have discussed so far. So we have concluded that any disturbance that we get on the tune node will result in reference spurs of some kind because it will be corrected with narrow current pulses which have a lot of energy at the reference frequency and its harmonics. So current mismatch in the charge pump, charge injection of the switches, charge sharing, leakage affecting the tune node, either through the varactors, the MOS capacitors, or even the charge pump transistors, all will lead to reference spurs. However, there are a couple of important other sources that I want to briefly point out. The first one is if we put everything on chip and, for example, we have a regulator to supply the VCO as well as the charge pump, and even though we do a very careful layout, we will always end up with a certain amount of impedance between the supply here of the charge pump as well as the VCO. This means that as the charge pump starts to pull impulsive currents, that we get a ripple of the supply of the VCO, and that again will result in possible reference spurs. Another mechanism, if we use off-chip VDDs and off-chip regulators, we still have to be very careful about the packaging and maybe bond wire or other coupling mechanisms in the package, because again, the impulsive currents that flow through this bond wire can couple onto the supply of the VCO, completely bypass the filter, and still result in reference spurs, as was also pointed out in an earlier lecture. And last but not least, in any approach, we are always faced by what noise that can occur on the ground node, and again affect and result in reference spurs in the VCO. Okay, so at this point, we arrived at, we completed the loop, and we are ready for some conclusions. I discussed the transistor level implementation of the critical PLL building blocks, primarily those building blocks that typically require a full custom design. I tried to link some of the circuit performance element or the circuit performance to the PLL performance, and I discussed some challenges in nanometer CMOS technologies, in particularly the size of the PLL and the VCO, the loop filter size, leakage that you can occur, and the low voltage operation that we need to accommodate in newer technologies. Finally, I want to comment that, of course, there is a lot of activity in trying to use digital gates to improve PLL performance. To a large extent, that leads to PLL architectural changes, or maybe can be used at the circuit level to do some additional calibration. For example, leakage. There are some examples in the literature of leakage calibration. Here is a set of references that you can use to go and look at some of the problems in more detail. And last but not least, I would like to thank my student Xian Yu for all his help, his inputs and suggestions in putting these slides together. Thank you.